Excellent. Okay. So, good evening to everyone in this call and everyone watching on Facebook and other uh, places. My name is Sean, uh, and I study at Cardiff University, and I'm going to talk to you today about the design of novel silicone materials, but from a bit of a chemistry perspective, because I'm a chemist. So, the first thing to think about is what is a silicone? So, a silicone silicone is not silicon, this atom here, Si. It's different. The polymer is prepared typically from siloxane monomers. So polydimethyl siloxane, PDMS, are the most common types. And this PDMS polymer is prepared typically by the hydrolysis of dimethyl dichlorosilane, which is this molecule here. The reaction is quite simple. You take N equivalents of the dichlorodimethyl silane and react it with N equivalents of water. What happens is you have this polymerization reaction going on where you form this PDMS, this dimethyl silane monomer, and you get a chain of, with a number of silicones in the chain is roughly equal to N, but you also produce 2N HCl's as a side product. Just to double check, are you seeing all the presenters across some of the figures, or
We can't
just
see the presenter. We can see the screen. So
that's good. That's
people
good.
are
Yeah.
looking at just the screen. Okay.
Okay, cool. Yeah, so then you produce two N equivalents of the hydrochloric acid. So the number of silicones in the chain is typically equal to N, but can be less or more depending on a number of factors, which I'm not really going to go into today. It's beyond the scope of this presentation. So why do we care about silicones? They're everywhere. So you've got domestic applications. You're looking at silicone baking molds, silicone bathroom sealant, in cosmetics, especially special effects in movies and theatre. You're looking at silicone brake fluid for cars, but also more niche applications such as stretchable electronics, which I've shown here. You've got drug delivery vehicles where you load drugs into the silicone and slowly release them or quickly release them, depending on your application. Super hydrophobic surfaces, which don't allow bacteria and other organisms to adhere to them. And also prostheses and implants, which is sort of my area of interest. So curing systems in silicone. So when a silicone rubber sets, it's termed as cured. So to cure some silicone rubber, you need a base polymer, a cross-linker, and a catalyst at a minimum. So three most common reactions here are platinum catalyzed hydrosilylation, a tin catalyzed condensation reaction, and peroxide cure. So I'm going to focus specifically on platinum catalyzed hydrosilylation today. So in this, your PDMS polymers are normally terminated either end with a functional group. In the case of the platinum catalyzed hydrosilylation, you need an unsaturated bond at the end on either end, so that's probably most likely a vinyl group. Your cross-linker is a methyl hydrosiloxane dimethyl siloxane copolymer. So the dimethyl siloxane is sort of an inert section, whereas the hydride from the methyl hydrosiloxane is the other part of the reaction. And you have a platinum zero catalyst. So platinum of other oxidation states is less effective. So to recap, hydrosilylation, a reaction between an unsaturated bond, a hydride, and a silicon component catalyzed by platinum. So how does this reaction proceed? You can do a bit of chemistry. So here's the hydrosilylation catalytic cycle. So I'm going to start off at our platinum zero catalyst. You put it in, and you get an association of the hydride-based monomer via an oxidative addition reaction. So that sort of splits along this bond here to produce a platinum 2 catalyst with the oxidation status 2, with a hydride bound here and a silicone bound here. Following this, you get association of the vinyl group at the ends of your PDMS base polymers, and that associates via a pi bond to the platinum 2. You then get what's known as the migratory insertion step, which is important, the important step really, where you get the migration of this hydride group off the platinum onto this CH group here on the vinyl, producing a methylene bridge. And you get a reductive elimination reaction, returning your platinum 2 back down to platinum 0 and forming your new methylene bridge from your vinyl terminated PDMS to your cross-linker. So this reaction can happen up to M number of times per polymer. So if you imagine if you've got, say, 20, M equals 20, you've got 20 of these reactions occurring along the polymer chain. So it quickly builds up a 3D network of siloxanes. So designing silicones, the principles you want to apply, you're going to start off with an ideal network where you have a system containing a cross-linker with a functionality, which is the number of reactive parts per molecule of greater than 2, and a base with a functionality of 2. So for the vinyl, you want a vinyl either end of your chain. So from this, you can calculate the stoichiometry, R, which comes in later in my descriptions of design the materials. So you have R is equal to F, the functionality, multiplied by the concentration of the cross-linker over 2 times the concentration of the base polymer. So 2 is the functionality of the base polymer. Of course, ideal networks are never ideal. Real networks are nowhere near ideal because you can have all sorts of interactions going on. So instead, we need to look at 2 parameters, which is RC lower and RC higher. RC lower is caused by the excess of your polymer base and is calculated by 1 over F, the functionality of the cross-linker, minus 1. Whereas RC higher is calculated as the functionality of the cross-linker, minus 1. So you want to stay between these 2 parameters in order to ensure your silicone network gels and you actually have a curing reaction take place. So when you're making a platinum cure system, you probably want to consider 5 factors: polymer type and molecular weight. You want to look at your catalyst, your cross-linker. You want to look at maybe having an inhibitor, but that's, again, beyond the scope of this talk, and an appropriate filler for your material. So polymers and cross-linkers. So high molecular weight PDMS polymers produce networks with greater flexibility. So if you imagine if your chain is like this, the short molecular weight will have less flex. The higher molecular weight will have a lot more flex to it. So you want to increase the flexibility there. Lower molecular weight PDMS polymers will again produce more brittle materials as well, more like plastic, so more similar to this red material here. And also lower functionality, so less reactive groups on your cross-linker will also make the material more soft. You want to look at including fillers, possibly, depending on your application. So most common is silica. What happens with the fillers, you have a lot of intermolecular interactions, and that increases the mechanical strength of your material, but it decreases the max elongation due to these intermolecular interactions. So it doesn't stretch as much, but it's stronger. Another thing, if you think about like desiccant bags you get when you buy anything and they're to absorb water, silica does that. So if your material is going to see a lot of water, it's going to be involved in a lot of aqueous environments, then you might want to use hexamethyl disilazane treated silica, which is hydrophobic and stops water absorption as well. Final thing to consider then that I'm going to go over is the catalyst. So it's got to be sufficiently active in this hydrosilylation reaction to produce rapid cross-linking. Otherwise, your material will stay soft. It won't form good networks. You want a platinum 0 center. There's other metals, but for the platinum catalyzed, you want platinum 0. Typically, you have the catalyst will have a vinyl siloxane component in the ligand, for example, this one, and typically a concentration of 10 to 30 ppm, so you're not wasting platinum because you don't want to chuck a load of platinum into stuff as it's quite expensive. So quickly, just to go over different types of materials you can produce. So this is where the stoichiometry comes in and the functionality previously discussed. A traditional silicone, you probably want your stoichiometry between 1.1 and 1.4 with a functionality of about 8. You want molecular weights between 20 and 70,000, and you want to include silica. If you want your material to be optically transparent, instead you would use a resin filler and you'd get rid of silica as it makes the material opaque. Whereas a low viscosity material, you probably just want to use a lower molecular weight PDMS. For soft silicones, you probably want to, for example, making an adhesive, you want your R to be between RC lower and a value of 1. High molecular weights and resin fillers, excluding silica again. Moderately extendable materials, you probably want molecular weights greater than 50,000, potentially some resin, no silica again, and a functionality of greater than 8 or 8. Whereas a highly extendable material, you probably want even higher molecular weights of your polymer, a functionality of between 4 and 5, just so it's really loose, and silica in low loadings to give it strength. So that's sort of a quick, brief overview of how to design silicones, and I'm happy to take any questions.